Hi, it's Ilya, and I keep explaining how I trained this robot to fold laundry as a part of ICRA competition LeHome challenge. This video is the last third part of the mini-series about this competition. This competition had two parts. The first one was in simulation. So we were provided with the simulation environment, and we needed to train the simulated robot to fold laundry. I won this simulation round, and among other 8 top teams, I was invited to Vienna to the ICRA conference to participate in the real-life final. In the finals, we needed to move from the simulation to the real life and train the actual physical robot to fold the actual physical garments. In this final round, I placed second, and today I will share all the details about my solution. I will talk about the human-in-the-loop DAgger style data collection, where we efficiently collect only correction data, very short intervals that allow our policy to overcome the bottlenecks and the main problems that it has. I will show you how to set up the real experimentation rig so you can both control your robot manually and run your policy and seamlessly switch between these two modes to collect a lot of intervention recovery data. I will also talk about sim-to-real gap and explain why it's not so trivial sometimes to move your policy trained in simulation to the real life, and explain what are the approaches, how to reduce this gap and how to make your policy work better, and how to mix different types of data like real robot data and simulation. And also I'll talk about some problems that you can face on the way. As I said, I already released 2 videos about this competition, but both of them are focused on the first simulation round, and they are talking about my reinforcement learning approach. And today's topic is kind of separated, so you can actually watch this video and understand everything that's happening here. But if you want a bigger picture and if you want to learn the whole context, then I would recommend you to watch these 2 videos first. And now let's begin. These are 4 types of garments that we needed to fold in this competition. And these are the frames from the original dataset provided by organizers. To give you a sense of the task, let's look at some rollouts from the original dataset. Similar to the previous round, the task is simply to fold given garments. But in this case, we care not only about the final success rate, but also about the partial completion. For example, in case of t-shirt, we get 10 points for each sleeve properly folded, and then another 10 points for the final fold. For a reasonable but bad quality fold, you get half of the point. So if you fold one sleeve but it's not very nicely folded, you will get 5 points for it, and it doesn't impact all other steps. For example, you can get partial points for one sleeve, then full points for another sleeve, and then full points for the final fold, and eventually you'll get 25 points out of 30 for this t-shirt. In case of shorts, you get, of course, less points, at most 10, and in case of pants, you can get at most 20 points because there are just 2 movements. And also, when you fold in the finals some unseen garments, you get 50% more points than for the seen ones. One important remark about my solution for the second round. I think that this competition was slightly imbalanced because we had much more time for the first round. So I personally spent around 3 months working on my solution. And for me, it was more like research project, when I experimented with different approaches, models, architectures, data collection, and so on. But then we had very limited time for the second round. So all the data sets and final rules and all other requirements for the second round were posted maybe 2 weeks before the actual conference. And also I needed to fly to Austria, that is on the other side of the world for me. And I spent like a few days on it in the end, the whole weekend. So eventually I had maybe a bit more than 1 week to actually work on the second part of the competition, as well as other competitors. So I didn't really have time to do the proper research or to experiment with different things or set up the whole reinforcement learning pipeline. For me, the second round was more like hackathon. So the first 3 months I worked in simulation to prepare some bit more fundamentally grounded solution. And for the second one, you just needed to quickly assemble some pipeline and make it work in real life. Again, so it was a bit more hackathonish. So I didn't manage to actually implement some ideas that I wanted, but I tried to implement the pipeline, the recipe that works, that shows some reasonably good results. You probably know I don't like to do a lot of ablations anyway, and in this case it was even less ablated. Again, I just try to do some very reasonable things fast as possible to get some results in 1 week. And in the end it worked, so I think I did right things, and this is what I'm presenting today. My overall strategy for this real-life round was following. I started from the model pre-trained on the simulation, so this is one of the latest checkpoints of my final submission for the first round. I believe that the latest one was a little bit overfitted to the simulations. So instead, I looked in the past and took one of the earlier checkpoints that already had a good results, but not the best in simulation yet. And then I simply added data from 3 different data sets. The first one is the official data set provided by the organizers and collected on the rig that is the most similar to the final evaluation rig. The second one is the simulation data set. So I still have a lot of data from simulation, and I try to align it as much as possible with the real data that we use, and used a lot of these simulation rollouts as a part of training data mix. And finally, I assembled my own rig to collect the extra data at home. I also tried to make it as similar as possible to the target setup, and I'll talk about it today. And then I simply collected data using my own robot at home. And then I combined all these 3 data sources with different alignment techniques and with different kind of extra step and corrections that I will mention in this video, and used it for fine-tuning. So I took this pre-trained model that worked in simulation already. I added a lot of data, specifically real-life data, and simply fine-tuned on it using straightforward behavioral cloning here. And as a result of this process, I generated this new policy that is capable to control the real-life robot. But then there is one more step that probably is the most important, and this step made my policy very robust and actually increased the quality a lot. Is a human-in-the-loop data collection, or DAgger data collection. So this is the process where you run the policy on the real robot and from time to time intervene to fix mistakes that the policy is making, and then add all of this data into your training mix and train it again. So I managed in these few days that I have to do a few cycles, few iterations of it. So like I trained my policy, I collected a little bit of extra data with human recovery, with human in the loop process. And then I added it to the training mix, train a little bit more overnight, and next day collected more data. I think I had time to do like maybe 3 iterations of it. And I've really seen progress. I've really seen that the policy quality is improving over time. And it definitely wasn't the limit. So I think it was very, very important things. And unfortunately, I didn't have more time to improve it even more. But I think it was one of the main factors that made my policy work very well. And here you can see the difference between different data sources. On the top is the behavioral cloning data set provided by organizers. And this is the one that is the closest to the evaluation setup that we used in the actual finals. And then the second is my teleoperation and DAgger data collection. So this is my setup. You can see that a lot of things are different. The robot looks different. Then, I don't know, wiring is different, and maybe sometimes policy can pay attention to it. The garments that I'm folding, they're slightly different. I try to align them as much as possible to what provided in the original data set, but I didn't have exactly the same garments. And then the colors, the lights, everything is very, very different there. And then if you look at the simulation data, of course, it's also very different. So again, they're not terribly different, but there are a lot of visual differences between them. So anybody can recognize which one belongs to which data set. And it was a tricky part to make sure that my policy can learn from all these data sources together and then generalize well to the final environment where we evaluated our policies. In the beginning, before I even started this DAgger loop, I collected some data using teleoperation, using my setup. And it's approximately half of what organizers originally provided. And then, as I said, in the next couple of days, I had a few iterations of collecting DAgger dataset with a lot of corrections, with focus on the harder cases. And this dataset is more or less the same size as what organizers provided. So this is the distribution of data that I eventually used for final training. But importantly, I applied different weights to different data sources. On this chart, you can see total amount of data that I collected using different ways. The original data from organizers had 500 rollouts. I collected almost 800. And then I also use 1700 rollouts from the simulation. If I would use this data as is, then this kind of best original data set that is the closest one to the target setup would be underrepresented in the data. And it's not what I wanted to do. So I wanted this data set to be actually overrepresented as much as possible. This is why I downsampled all other data sets. My data set that I collected at home was downsampled around 5 times. So I sampled frames from these 800 rollouts as often as if I had only 200 rollouts. There was kind of high variety of data inside them, but I didn't sample them too often. And of course, I downsampled simulation data much more. I downsampled it 20 times. So basically, I had a lot of different simulated rollouts, but I sampled from them with much lower probability. And again, it's very intentional. So I wanted this like 10% of data, final 10% of data that exists in every batch to be from simulation. I want this data to be very diverse inside this 10%. I want it to be from many different rollouts, but I don't want this data to dominate the training data because then it will overfit the simulation. So this was kind of my logic. So keep the data set that is the closest to the final setup at 60% of every batch on average, and then provide a lot of correction data that is collected to some similar setup but with my home robot, and keep it around 30%, because I didn't want policy to overfit to this format, but I wanted it to learn some nice recovery behavior from this 30% of data. And then finally, this extra 10% of simulation data simply adds a lot of maybe diversity and a lot of like different cases that I believe just helps policy to extrapolate even further and again be more robust in the end. I didn't start to train the model for this part of competition from scratch. Instead, I just reused the one that I trained in simulation. But because I changed the way how I train my model and also I changed the data that I use for the training, I needed to make some adjustments, and I needed to actually remove some parts of the architecture that I used in the first round. So I talked about this architecture a lot in the previous videos, so I will not repeat myself. But what I will explain is what was removed for the real life round. The first thing that I removed are multiple auxiliary targets because they just didn't make sense anymore. First of all, I removed everything that's related to success probability. It's like either success probability right now or success delta given our actions, because for the training in this part of the competition, I used only successful rollout. Whole data set that I used has a label 1 for success, and it doesn't make sense to train anything. So I simply removed this part. And as I switched from training in simulation to training in real life, I removed key points, distances, predictions, because this is something that relies on the privileged information from the simulation. And when you train your policy on the real data, you simply don't have this data from the simulation and you cannot generate this target. So obviously I also removed them. In the end, I left only garment type and completion prediction. Garment type we know, of course, and we still need to predict it. And completion, I would say, is not so important because I'm not using reinforcement learning anymore in the second round. But still, we can predict it, and it doesn't hurt to have this extra auxiliary loss. So I just decided to leave completion as a part of the model. And the second big thing that I removed is advantage input. A quick reminder, this input was used as part of recap. That is the reinforcement learning approach. And again, as I'm not using reinforcement learning anymore in the second round and just doing some fine tuning, I don't need it anymore. And also I don't have any advantage because I use only successful rollouts for training. It's much harder to predict advantage or use something similar. So I completely removed it. And of course, I removed all the logic, all the inference time optimizations that depend on all these things that were removed. So for example, I don't have this best of n selection anymore because I cannot predict this delta success. I don't have classifier-free guidance because I don't have advantage and advantage input. So the overall pipeline, kind of the model architecture, became a bit simpler because there is no reinforcement learning part and there is no part that depends on the simulation. But the rest of the model stayed basically the same, and I simply fine-tuned it more on the real-life data. Before we go deeper into the sim to real discussion, I want to give you a slightly embarrassing, I would say, example of the gap in perception when you deal with simulation only. So, as I said, I spent around 3 months working on the simulation part of the challenge. And during this simulation, I trained the model, I experimented a lot, I've seen thousands of rollouts probably. And I was sure that we are folding something normal size. So I was sure that we are folding normal size claws. But then when I needed to actually assemble the rig and I put these two arms at the distance that they're supposed to be at, it's like around 46 centimeters. So it's like maybe something like this. I realized that no way I can fold my pants using these arms. So like if I put my pants here, they will be longer than this table. So no way this arm has enough range to do it. And moreover, when we like look at the actual rollouts, the pants are right in front of the arm and they maybe take this space. And this was the moment when I realized that, oh, we are actually folding kid-size clothes. It's not about the adult size clothes. Everything is kid size just because these arms are actually pretty small. And if they are kind of located like this, you cannot really fold all the different types of garments. So when we talk about pants, these pants look like this. So this is kid size pants. They're approximately this size. And then there is enough reach for this arm to do the whole folding. But when we deal with kind of the proper sized one, they will not be able to do it without actually moving these arms that wasn't allowed in the competition. So yeah, this was pretty big discovery for me after 3 months working on this problem. It didn't really change anything, so it didn't change anything in my approach or solution or so, but it just shows that when you just look at the pictures and you don't touch the robot and the problem in real life, you can actually don't even understand what you're dealing with exactly at this point. So I definitely recommend you when you work on the real problems to be like close to the actual robot, to look at how it works in real life, and it definitely will close some obvious perception gaps that you may have. And yeah, for this competition, then to actually collect my data, I needed to ask a few of my friends who have kids to give me some kid clothes. And then also I bought some cheap kids clothes just for this competition to collect my data because I couldn't use mine for any of it. Let's compare some episodes from the real round training dataset and the simulation one. You may see that there are a lot of differences. Some of them are very obvious, like camera resolution, the position of the camera, color of the robots. The garments themselves and their physics are also slightly different. Even so, the simulation is pretty good. Again, there are a lot of differences between simulated and the real life. There is also some extra multimodality introduced. So for example, in simulation, when we fold the t-shirt, we start from the right sleeve, and in the real life, in the dataset, it starts from the left sleeve. A similar multimodality is introduced for the pants. So in simulation, you can see that we start from the top, and in real life from the bottom. So these are slightly different techniques how to fold these pants. Shorts is the easiest garment type, so it's folded in just one movement, so there is no other technique how to solve it, and they're aligned between simulation and the real life. But in the simulation, they are always rotated the same way, and in real life, the two different 180 degrees rotation were introduced. So it's another extra thing to take into account. Having these different ways to fold laundry is not necessarily bad. If I would need to like train the real production robot to do laundry folding, maybe it's actually a good idea to try different approaches, to try to train model to do it differently, and maybe it will learn when to use different approaches and so on, and we'll be able also to recovery for some harder cases. But in this particular competition, I didn't want to introduce this extra multimodality. I don't want my policy to stuck while thinking whether it should start from the left sleeve or the right sleeve, and so on. So in these cases, when you need to quickly train the model to do some task, it's much better to keep just the one way of completing this task. Then it's just much simpler distribution of actions that your model should learn. And here I wanted to align it as much as possible. So when I collected my own data, I tried to do it the same way as organizers did in their data set that they provided. And also in the simulation, I removed the parts of rollouts when kind of the simulation style of folding is different from the folding in the real life. So in this case, at least all the data sources use the same approach to solve the task, and it's not confusing for the model. This is my full data collection setup for this competition. And let's discuss it step by step. First of all, there is this area in front. This is the main area where everything is happening. I have two follower arms there. Each arm can move in any direction. I completely can control it. And each arm has its own wrist camera. So I can collect the video from these wrist cameras for my policy. And of course, there is a garment over there that we fold using this arm. Also, I have this top view camera. I'm using the RealSense camera that can also collect depth information, but I don't use depth at all. I just use only RGB image here, so you can use any other camera on top if you want. The only reason I use RealSense because I have this RealSense and it's the closest one to what organizers used in the setup. I tried to make it as similar as possible to the setup from organizers. So for example, I made this white background. I printed orange grippers. I was lazy, I didn't have time to reprint the whole arm, so I printed only grippers. At least on the wrist cameras, they look the same or very similar to what organizers have. Again, I use top camera that is different from what they use, and it actually has different field of view. So I needed to adjust it quite a lot to make it aligned with what was in the original data set and what was in the final evaluation setup. But yeah, I will talk about it a bit later. I even implemented some tools to make these adjustments easier. And of course, all the distances, so all the positions of the arms should be pretty much aligned with what is provided in the official guidelines. The second area is the operator area where I stand right now. And here I have two leader arms. I put them on this adjustable table so I can move it up or down and make it the most comfortable way for me to teleoperate. And of course, these leader arms, they're connected to the follower arms. So whenever I move them, the follower arms also move, and this is kind of the whole point of teleoperation, that I can control my robot from here by moving these arms. All four arms and all the cameras that I use are connected to one computer right here. And this is my kind of main workstation, and it also has a powerful GPU because I want to run the policy and be able to control my robot using this policy during the data collection. It would be much harder if I just connected to my laptop. So I use this computer for now. Usually when I use this computer, it just stands in my corner, like most of the time it's just right here, and I never connect any monitors or keyboards to it in the normal days. I simply use it as a cloud server. I SSH to it from my laptop and do whatever I need for, let's say, like training or some other GPU usage. But in this case, it makes total sense to directly connect everything to it and to use it as the main machine. And this is why I also added this monitor. So I have this small portable display. It's connected again directly to this computer, and I can see some things using rerun. That is the default visualization tool in the robot. So whenever I control my robot, whenever I do anything, there is a kind of picture in the run that is changing, that is showing what's happening, and I can use it for some kind of debugging to make sure that everything is working fine and my data set was saved correctly. Important notice, so it's a good idea sometimes to teleoperate only using the picture that you see on the screen. But I don't think that it's actually necessary. So it's necessary to make sure that you can teleoperate using this picture. So it's important to kind of know that it's possible. But when you actually teleoperate, there is nothing actually so bad if you operate it by looking at the actual robots. Again, it can depend on the setups. If you are in doubt of your camera setup, it's better to look at the cameras and try to teleoperate using only them. But if you already know that your setup works well, quite often it's okay to actually look straight on the robot and teleoperate it like this. Here I also have a keyboard, actually just in case. I almost never use it. As I said, I usually don't even connect it to my computer. Right now we just have some UI on the screen, so I decided to have it here. And from time to time I need to type something, but 90% of the time I don't really need this keyboard. And of course I use my laptop. This is my kind of main client. I actually connected to this computer to my laptop right now. And whenever I run anything, I simply run it on my laptop. Just make sure that whenever I run anything in console, it's opened in the display when I need it on the real display. So you need to just make sure that you're redirecting it properly to the monitor if you need it. But generally, this is my main device that I use to control everything, to write code, to change parameters, to actually run things. And this is why it's right here nearby as well. And a very important thing that you actually don't see right now, and this is the highest ROI that you can add to your setup, is this pedal. So it's pretty cheap plastic pedal that is connected by USB to my computer, and you can program it however you want. You can assign different keys to each of these pedals, and whenever you press them, it's simply equivalent of pressing the key on your keyboard. When you actually teleoperate in the robot, your hands are busy, so you cannot really click a button like to move to the next episode, or to save this episode, or record, or pause, or anything. But you still have your legs, so you can use your feet and you can click the buttons on the pedal. And it's extremely convenient whenever you teleoperate this bimanual robot, especially when you need this DAgger-like data collection, when you need a lot of intervention, when you need to go to the next episode or reset something. This is really, really helping. I think 3 pedals are probably optimal. Maybe if you have extra parameters, you can have even more. But for the simple human-in-the-loop data collection, it should be enough. One thing that definitely can be improved is cable management. I have probably 8 different USBs connected to my computer, and then I have 4 power sources, I have 1 HDMI cable, and so on. So ideally, if you set up something for like long time, it would be nice to organize all these cables a bit better. I again just did it for 1 week, so I did it somehow, and it actually works. So I didn't have so many problems with it. It just looks a little bit messy, but overall it's fine. And that's it about my setup. Again, you can use my code that I already shared to do everything that I'm showing here, to connect all your robots and to kind of control them this way. Also, I have a very old video about these arms where I explain how to set it up for the first time and how it works. So if it's like something very, very new for you, I would actually recommend you to set up like 1 arm with simple teleoperation and try it first before you doing something like this. So yeah, you can also watch my video and follow these initial steps, but setting up this thing is not much harder, to be honest. It's almost the same, just add 1 more arm and then a couple more things for convenience. And this is not some special robotics lab. I just do it at home. So this is my working table, this is my dining table. I have this computer with GPU, and this is what you actually need for this. And as well, you need these bimanual robots. But if you have it, you can reproduce it and you can run all of it at home, because everything else are just details. SimToReal is just one example of the training and the evaluation alignment. So in practice, you can have much more cases when you train your policy on some set of data using some setup, but then you want to evaluate it on another setup, maybe on another robot, maybe in another environment, maybe again it can be sim to real. But the case when you use different environments for training and evaluation are pretty often. And on the high level, there are two ways to resolve this difference. So the first one is to align everything as much as possible. So to make your training distribution as close to the evaluation distribution as possible. And the second one is diversify your training distributions. Increase the variety of data in your training distribution such as it eventually covers everything that can happen in the evaluation distribution. And in practice, there is no reason to choose between two of them. You need to try both of them. So you need to try to align your training data with your target evaluation data as much as possible. And when you reach the limit, when you cannot align it even more, you should add extra variety into your data, such as it covers more cases, and hope that it will cover all the cases that are represented in the target evaluation setup. To be able to use simulated data for the training, I needed to record it in the same format as the real live data. I took the successful rollouts that I already had and ran it through the simulation again, but this time I recorded it with different resolution, with orange colors of my arms, and with different position of the top camera that is more aligned with the real life data set. And now let's discuss how it looks in the real life scenario. So in this particular case, in the competition, we have this target setup, target rig that organizers set up on the conference side where all the evaluation during the finals happened. And the closest thing that we have to this setup is the data set that organizers provided. So they used the same arm, the same cameras, and everything was the same, but it was recreated somewhere in their lab a few weeks before the actual competition. So it wasn't exactly the same as during the conference because of the lights and some other things, but generally it was very, very close. And I tried to reproduce it as much as possible, and there are some simplest things that, of course, I did. So first of all, I used the white background. I used very similar garments. I used very similar robots, even though they're different colors, but these are kind of the same robots. There is the same position of these robots. They have the same distance between them. There is a top camera, so this kind of basic setup is the same as our target setup. It would be very strange to use something very, very different. The next thing is slightly harder. So the arms that were used in the finals are orange, and I didn't have orange arms. I had only these red or yellow arms. And I had orange filament, so I could print it, but it would take a lot of time to print and assemble everything. So I decided to print only this part, only gripper. And I think it was pretty much enough because at least for these two cameras, for the wrist cameras, they see only gripper. They don't see the rest of the robot. And for them, the picture became very, very similar. So the top camera would see red robots instead of orange, but it's probably not such a big deal in this case. Also, for this arm, there is no standard default camera or camera mount. So I needed to try different options. I printed multiple camera mounts. I used different lenses for my cameras. Eventually, I think I managed to match them pretty well with what organizers use, but still there is some difference. So I think my cameras have slightly wider field of view. So image is not exactly the same, but it's pretty close. The hardest part was the top camera because I don't have the same camera as organizers. This RealSense is the closest to it, but still it has different field of view. And it was pretty hard to align it with the actual robot and the actual setup. To make the alignment of the top camera easier, I developed a special tool. I'm running it right now, and what it's doing, it's taking a random frame from the original training dataset, and then move the arms exactly to this position from this frame, and then shows me on the screen the overlay of the images from the training data and current stream of the cameras. So let's move to the next state. Let's say, so I selected some state that randomly moved this arm here. And right now on the screen, I can see this arm overlaid with the original arm in the training data. And I can see that the left arm is almost fine, but the right arm, for example, is not matching. And I can try to move everything to achieve better match. I also can try to, I don't know, move the camera higher, release it a little bit, move it higher, move it lower, move it to the left, to the right, rotate a little bit, and then find a setup that looks a little bit better. Again, this is not the perfect setup, but it's slightly better. And then I can select another random state, another random position from the training data and see that, oh, actually it's still not aligned. You can see that left arm is significantly misaligned. So I probably need to move camera a little bit lower, change a little bit an angle, and overall experiment with it, like and move it around. And this is how I actually did this alignment. So I developed this tool, because without this tool, you can end up like having something like this, that it's, I don't know, like this, that is very, very off, and you will never know until you compare this to pictures. But with this overlay, you can achieve pretty good result, even if it's not perfect, but you can achieve pretty good result. And this tool turned out to be pretty useful, and not even for me, but for other participants and organizers, because eventually when competition started, they also have the same problem, that it's very hard to set up the camera, to put it in the same position as it was when they collected the training data. So I actually provided my script to both organizers and other competitors, and everybody used it to set the environment during the competition. So I think it was a pretty nice tool. Okay, so it was about alignment, but I always knew that I couldn't really perfectly align everything. So first of all, the arms can be a little bit miscalibrated. So these arms, they usually have a very big backlash. So I can like shoot them like this, and it's basically the same state for them. Also, when you calibrate these arms, it's kind of manual process, and you may be like rotated it, not the whole range of motions or something like that, and then they're miscalibrated by a few degrees and so on. So every time when you recalibrate this arm, it's slightly different. It has slightly different parameters. And there was no way to actually calibrate them perfectly. So what I did, I recalibrated them many times during data collection. So I every day basically run this calibration. It takes like 1 minute if you know how to do it. And every time I had slightly different calibration. So my policy didn't overfit to this particular setup. Another thing that I did, I slightly moved them a little bit and rotated. Also, I switched these two arms a couple of times, because again, these are cheap arms and they can have some differences, maybe during printing, maybe because of the motors, maybe because of something else. So just flipping two arms is already a little bit of randomization. And of course, you may see that my camera, my top camera, is not very stable. Yeah, I can move it around, I can rotate. If I touch it like this or shift it, it will be in the different position. And if you try to train some very simple policies before, you probably notice that the camera position is very important. You rotate camera a little bit, you move it a little bit, and your policy starts failing. I expected again that my camera will never be in the perfect position, and also during the finals, I didn't expect it to be in the perfect positions. So I wanted my policy to be robust to different positions. So I actually, on purpose, miscalibrated camera multiple times. So I did something like this. I now rotated, moved stuff around, and then just calibrated it from the beginning every single time. And every time calibration was slightly different. So the final point or field of view was slightly different for the camera. And it's completely fine. So maybe for the first time it was a little bit noisy and policy didn't work very well. But after I did a couple of times, then policy started to be very robust to it. And eventually I think it helped me a lot, because my policy really robust to this camera movement. Even if I move it by a few centimeters or rotate, it still works pretty well. And this is exactly what I wanted to achieve in this competition. So I knew that camera setup will be different from whatever I set up at home. And this is why I trained it to be pretty robust to the camera changes. And I think it worked very well. And I think it's very important for the practical application. So when you train the real robot that is supposed to complete some real task, you don't want it to be like very, very overfitted to particular setup that you have. And you probably want to introduce some noise. You want to introduce some changes in your environment to make policy to learn to be robust to these changes. I also created a very similar tool for the simulation and real alignment. And this tool is doing very similar things. It just takes one episode from the real life training data set and kind of replay it inside simulation. What we care about here is the overlay of the arms. And this tool allowed me to change the parameters of simulation, specifically the camera position, to make sure that the images generated from simulated data are very aligned with what we see in the real data set for the real robot that we train our policy on. Another dimension that requires alignment between different data sources is speed. You can complete the same task in the same way using the same approach and so on, but let's say one operator will complete it 2 times faster. And it also introduces a lot of multimodality for the model. Because when the model predicts the next chunk, it will need to somehow choose between the slow chunk and the fast chunk. And we don't want to introduce this confusion to the model. This is why I decided to apply extra speed coefficients to different data sources. So the original organizer's data source is a baseline. I don't apply any coefficients to it. And then my original data set that I collected using teleoperation at home is actually slower than the organizer's one. And I applied 1.5 speed up coefficient to it to align the speed that I used to collect my data and the one that organizers used. The simulation is the opposite case. Because of my reinforcement learning, my policy actually learned to complete the task in simulation very, very fast and significantly faster than what either organizers or I could do in the real life. So I needed to slow down my simulation replays. And then finally, DAgger data collection is some mix of policy rollout and manual rollouts. Especially in the beginning, policy was pretty slow when I did these rollouts, and the policy actually maybe was 2 times slower than the initial data set for it. So I needed to speed up the data collected by the policy. And also, when I need to intervene, I usually need to intervene in the hard cases, and I also try to move slower in these scenarios. And my speed was also pretty slow. So eventually, I ended up kind of speeding up my DAgger datasets around 2 times. And then in the end, I actually implemented this speed up factors on the dataset level, not just dataset type. So for example, my latest DAgger collection was much faster and I used much slower factors. So I started to change it. But these are high level initial speed up factors that I applied to different type of data that I used to train my policy. Let's quickly talk about augmentations. I already talked about it in the previous videos, so I will not go very deep, but the idea is that this is the training time technique that allows you to introduce some disturbance into your inputs, and it makes your policy even more robust. Again, in my case, I knew that I'm dealing with some very, very shaky, let's say, setup. And during the final evaluation in the conference, there can be some problems. I don't know, the lights can be different, the colors can be different for some reason, and so on. And maybe we will deal with some, let's say, garments that are different color, or maybe something else will be off. So I knew that there can be a lot of problems. So this is why I applied pretty heavy augmentations in this case. And you can see examples in this picture. So I just generated it from the training config. In the left top corner is the original image from the organizer's training dataset, and all other images are different augmentations that were randomly applied, and they represent the input data that my policy actually got during the training. You can see sometimes it's adding some blur, sometimes it's changing colors, sometimes it's changing some white balance, and so on. And some of them even have this cutout augmentation where I simply close the part of the image with this gray rectangle. So it's the same image all the time, but a lot of changes applied to this image before feeding it into the model. And I believe that applying these augmentations during training made my policy even more robust. Another story from this competition, and this time it's about one annoying bug that I introduced. So we have this robot, and this robot has multiple motors, and the position of each motor defines the state of the robot and defines the actions that we predict. And interestingly, most of the motors have range of motion close to 180, sometimes a little bit more. Yeah, you can see that every motor can go around 180 degrees in total when we try to move. And there are different ways how we can store the information about the current motor position. So one approach is to store the degrees, so radians, and another approach is to compute the full range of motion and kind of store the percentage of this range of motion every time. So for example, this one would be 0, this one will be plus 100, this one will be minus 100, and then we just adjust it based on the actual robot position. And the problem is that I used the robot library, and the robot library in the past changed the way how they store this information. Or they kind of support all the ways, but they changed the default way. And I didn't know it. So I used, in my code, I used the version of the robot that is a bit older than what organizers used. And we had different defaults. So it means that when I recorded my data, everything was stored in this like range of motion units. But when organizers recorded the data, everything was in degrees. And because most of these motors have almost 200 degrees range of motion, and there is like this 200 degrees range of motion in my units, it's very hard to see because most of the motors will be very, very close. Maybe there is like, I don't know, 10% noise in the positions, except maybe like one position. So this one is rotated 2 times less than it should be. But I couldn't understand it. So like I looked at it, most of things are very, very aligned except one joint. And I just saw that, oh, maybe in the training data, it's miscalibrated with just half of the range of motion or something like this. So I knew that something is off, but I couldn't figure out it. And for a significant part of my experimentations, I collected data in the wrong format. I applied some corrections, I applied some fixes. I divided the position of this motor by 2 and so on to make it aligned. But everything like looked very, very hacky. And again, I didn't know that this default behavior was changed in this newly robot version. And then I found it and realized it maybe 2 days before the end of the competition. Then eventually I fixed it, and the latest rollouts were collected correctly. But again, it took a lot of my time to fix it and find this bug. It also reduced the quality of the data that I collected because I needed to apply these fixes that are not really precise. So maybe actually to some extent it helped a little bit to generalize to the issues with calibration of the robot, but I think it's harmed me more than helped. And maybe even like this one bug cost me the first place. But again, I don't know. But anyway, this is just example of the bug that I faced. And when you use some libraries, also make sure that you check the default values and you check the differences between different versions of these libraries, because again, for me, it was a very big waste of time at least, and probably the quality of my policy in the end as well. And now it's the most important part of this video. It's DAgger data collection, or you can also call it intervention collection, or maybe human-in-the-loop data collection, and so on. And before we go to the actual examples, let's discuss why we even doing it. Our task has some initial state where we start from, and it has some target with maybe some variance. So we can consider different states as valid targets and different states as starting points. And also, usually there are multiple ways how we can complete this task. Again, in our case, there are multiple ways how we can fold some garments. If our initial data set has examples only from one of these ways, then of course our policy will also learn to replicate this behavior and will learn to complete this task using the same approach. And sometimes it will completely solve the task, but sometimes it will fail because quite often policies are not perfect. And now we want to collect more data to make our policy even better. And let's consider a couple of options how we can do it. The option number 1 is to collect more data from another mode, from another way to complete the same task. And it can be pretty good approach if you're training a generalist model and you want your model to be able to complete the task in many different ways. But if you are training like more simple model that is solving only one problem and you want to solve it in one particular way, then this approach will create more problems because our policy will start confusing different modes and will start to apply some steps from one mode when it's actually following another mode, and we can see new mistake patterns. So there is no guarantee that collection of this data will improve your policy performance, and sometimes it can make it worse. So the general rule, we want to stay very close to the existing distribution of data when we collect new examples. But collecting the whole trajectories is not a very efficient way. Again, if you look at this example, our policy actually doing a good job most of the times. Probably knows what to do in 90% of cases, and there is only like small subset of states where it's not sure what to do, maybe because we didn't have enough data there. Or maybe this part of the task is actually the hardest one, and you need to be very, very precise, and there is like very, very narrow range of actions that will lead you to success, or maybe there are like any other reasons. In any case, the point is that your policy can be good most of the time, but there are some bottlenecks when it makes mistakes, and these bottlenecks are most important areas where you want to collect more data. So basically, when policy starts to make mistake there, already make mistake and go out of distribution, you want to provide some corrective behavior, some steps that return policy back to distribution, back to the states where it knows what to do next. And this is why this approach, however you call it, human in the loop, intervention collection, DAgger data collection. So this approach is very, very efficient. You collect only the most important data. You don't waste your human time on collecting the data for the cases where policy already knows what to do. You stay very close to the original distribution, and you really help your policy to improve in the areas where it needs this improvement. So this is a very, very efficient and nice way to collect extra data. This logic is also very similar to how conceptually reinforcement learning works. So in this case, any rollouts, any steps close to bottleneck that are correct will have very high advantage. The steps where kind of policy makes mistakes around bottleneck will have negative advantage, and most of the steps outside bottleneck where policy just always completes the task will probably have advantage close to zero, and eventually your reinforcement learning will kind of do very, very similar things but in more automated way. And enough theory, let's go and look how I actually collected this recovery data in practice. The idea is the same. So we have a policy that is already pre-trained, maybe as behavioral cloning, maybe using a couple of iterations of this human loop data correction. And what we want to do, we want to let this policy to complete the task. And I will be standing here and just watch it. And whenever I see that it makes any mistake, I will take control and do teleoperation instead, fix this mistake, and then we'll give the control to the policy again. So let's see how it works. As I said before, I use pedal to control the process. So whenever I click the pedal, it gives the control to the policy. And now we will see how the policy is trying to complete the task. So it's trying to grab the sleeve on the right. And I think it's making mistake, or at least let's pretend that it's making mistake. Okay, so it made mistake. So now I clicked it again, and I have manual control, manual teleoperation. I can help it to grab this sleeve, and I click this pedal again, and now it's controlled by policy again. So you may notice that these leader arms, they are moving together with the follower arms. And it's not a bug, it's feature, so they are always in the same position. So whenever I want to take control, let's take control again, I don't need to move my leader arm to the position that I need. They're already there. So I can simply make a very, very simple corrections without any jitter, without any jumps. And this correction, as you may see, takes just a couple of seconds. And by the way, whenever I make any correction, this correction information is also saved into the dataset. So in dataset, you may see what episodes, what steps are made by policy and what steps are made through the teleoperation. You see right now, policy is doing very, very well. I hope it will complete the task. So yeah, it's successfully almost folded this garment. And when the task is completed, and when, in this case, let's wait until the arms will return, I just click the pedal again, this time another button, and it saves this episode. So now it knows that episode is successful and saved to the database. In another case, if something goes wrong, I can also click the left button on my pedal, and then this episode is simply not saved, it's completely removed, and re-recorded again. So in this case, I make sure that if, again, something went completely wrong, for example, I know sometimes the arm got disconnected or something just goes off, it doesn't make sense to keep this episode in the data, so I can just remove it right during the recording. And everything else is saved and stored and ready for training. And this is it. I just did it for many hours to collect many episodes with different garments, with different clothes, with different types of garments and so on, and used it for training. And I've seen that model getting better and better and better every night. So when I kind of one evening collect some data, I see that my policy makes the same mistake again and again, and I don't know, correct it 10 times. Then I leave it training overnight. I come back next day, I run these rollouts, and I actually see that policy learned my movements. It's doing exactly what I did during correction. So it's very, very nice. It's very, very powerful. I think this way of collecting extra data is maybe the best one for teleoperation, because you really collect the most important bottleneck corrections for your robot that policy doesn't know how to deal with. Another small comment, when I posted videos of my robot doing these things, some people said that it's a bit jittery and it's jumping a lot. And again, it's not a bug, it's my deliberate choice. There are ways to make it move more smoother, yes, but I didn't do it because they don't usually increase the success rate, and the only goal of competition was to increase the success rate, so I didn't need to make it look nice, and this is the only reason I didn't do it. So if you do it for like real application, it makes sense to look at this and try to predict some smooth trajectories, deal with latency and so on. But again, in my case, I just didn't need it. This is why I didn't use it. Now you can see some examples of the rollouts that I collected using this DAgger approach. For this demo, I selected episodes where there are a lot of interventions, but of course, by the end of the training, I did less and less interventions, and the policy was more and more autonomous. So you may see that most of the time, the policy works autonomously, and it can do significant part of work, but sometimes it makes mistakes, and these are the exact bottlenecks that we want to fix. Because your policy can be like correct 90% of the time, but makes mistakes in this 10%, and this 10% will lead to the fail because they don't let you really complete the task. If someone tells you that the robot works 95% of the time autonomously without interventions, it doesn't mean that accuracy of this robot is 95%. It can be 0 if this 5% where you need interventions are actually critical. And this intervention, human-in-the-loop data collection, is exactly what helps you to collect the most important training data to fix all these issues. And this is also one of the reasons why many robotics companies want to deploy their robots when they're not fully autonomous and still use some teleoperation, because this deployment really helps them to see when the robots make mistakes and collect the correction data exactly when these mistakes are made. I'm telling you that I'm not using reinforcement learning and I don't have any kind of advantage, but we can extract some of this advantage kind of information from the human feedback when we collect human-in-the-loop data. Let's say my policy is trying to complete the task, and for some reason I decided to intervene. Most probably, I intervened when policy did something wrong. So it means that for the last few seconds, it probably was doing something wrong and maybe already made a big mistake or maybe very close to making this mistake. So most probably the kind of period, few seconds right before I intervened is a bad period. So policy was doing something wrong. Then I intervene. It means that I provide the data that shows how to recover from the states that policy doesn't know. And this data is very valuable. It's probably very, very high advantage data because this policy most probably would fail, but with my correction, it will complete the task successfully with high probability. So my interventions are very, very valuable, and I want to give higher weights to them. So eventually I ended up having these heuristic weights for different types of data collected using DAgger. I used some baseline weight for the actual actions that were done by policy, and then I reduce weight for the actions 5 seconds before the intervention, and the intervention itself gets very, very high weight. So again, it's not exactly reinforcement learning, but it's very, very close to this advantage weighted regression that I used in the first round. It's not the true advantage in this case, it's just some weights that are based on the human feedback. Now let's go back to the simulation part and discuss the topic that I kept delaying for a very long time. I discussed most of the logic related to the simulation in the previous videos, but I deliberately moved this part to the last video, the video about the real life part of the competition, because I think it's very connected to what we are talking about today. Basically, this human-in-the-loop DAgger data collection is possible in simulation as well. As I mentioned before, I didn't manage to make it work really well, so this is why I didn't actively use it. But actually, I developed a lot of nice machinery. I developed a lot of nice tools to deal with it. And I even started to collect some data. The only problem was it's really pretty hard, so I didn't manage to collect it nicely. I probably need more training, and I just decided to focus on different parts of the solution. But I want to show you what I developed and how I use it, because even so it's very, very similar to how it works in real life. There are a lot of specific features and a lot of things that you need to think about when you're developing it in the simulation. Generally, you want to optimize this process as much as possible, and simulation gives you a lot of opportunities to do it. You may see that my setup is very, very similar to what I used for the real robot. The only big change that I made, I replaced the real robot with my TV. Again, as I said, I don't have a monitor. I usually don't use standalone monitor when I work at home. And I have only this small one that definitely not suitable for the collection of extra data. So I just use my TV. I just brought my TV here. And of course, when I actually collect data, it's just turned directly to me. Now I turned it under some angle just to make it easy for you to see what's happening here. But the idea is the same. You just replace the real robot with the simulation of the real robot. And the rest stays the same. So how does it work? Technically speaking, you can use IDAG directly to connect the data. So it has some UI. You can show different views. You can control your robot using these follower arms directly there. But I think it has some limitations, and I prefer to just develop my own UI this process because I managed to apply some optimization on top of it. So my leader arms are the same as before. They're connected to the same computer and they send basically the same signals as before. The only difference is that these kind of signals are applied not to real robot, but to robot that is running on the simulation. On the TV, you can see my interface. Here, I simply show all the images from all the cameras, and I also added these small robots models in the corners to actually see the state of the robots right now. This is something that policy has access to during the rollout, so I also want to see it on one screen and be able to kind of have this feeling, spatial feeling of the robot. Also, they help me with debugging in the initial stage when I just developed this tool. This tool allows me to load any hard state that I want to correct. And I will talk in a few minutes how I actually collect these hard states, but the point is that I'm already preloading some states that are not very simple and that really require some recovery behavior. And then I can take control, record some short clips with me controlling the robot, and move to the next clip and move to the next state to record the next one. And now let's see how it works in practice. Again, to start, stop, switch to the next episode and so on, I'm using this pedal because it's very convenient. So when I click it, on pause, I resume the recording. And you may see that when I move the leader arm, it's moving there as well. And you can also see a bit of problems here. So there is some lag, there is some latency, and also FPS is around usually 10 to 15, sometimes a little bit higher, sometimes a little bit lower. But anyway, you can see how the arm is moving here. You can see the small arm is moving on the screen as well. And basically, I can control it as I'm controlling the real robot. But as I mentioned before, I'm really bad at controlling the robot in simulation. So I will try to grab one sleeve and put it here. Probably it's not very nice, but it works. So I can touch the garment and basically do whatever I want with this garment. And ideally, I need to record some nice behavior that doing something good or correcting the mistakes, but now I'm just showing how it works. And at any point, I can stop it again, so I can pause it, and I can resume if I want, or maybe, I don't know, I want to change the way how I hold the arms or something like that, or maybe, I don't know, just something is off and I want to pause it, but generally I don't need it because I collect very short recordings, very short correction patterns. And then after I finished, so for example, I decided that I completed everything and I corrected the behavior, or the opposite, I completely failed everything, I click one of two buttons. So one of the buttons will reset it completely and didn't save it. Another one will switch to the next garment. And now these garments are selected randomly. So I just click and get a new random garment. But there is also mode in which you can select only particular garment or only particular garment type, or maybe sample it from some particular list of failed states, and so on. And one very important thing is that there is absolutely no latency when I load new garments. So you may see that I can start working with this garment, do some stuff, and then switch to the next garment, and it's available immediately. I just unpause it, and I can deal with it. And it's a very kind of big improvement that I developed, because actually it takes a few seconds for garment to load in simulation, and I did optimization that allows me to run multiple simulations simultaneously, and these simulations are preloading garments for me while I'm still dealing with the previous one. For example, you can see that there are 3 simulations right now, and all 3 of them have ready to use garments. So I just switch to the next one and it's available immediately. I can switch one more time and it's again available immediately. But if I switch, let's switch again. But sometimes if I switch too fast and the garment is not ready, I need to wait a few seconds. Without this, without having multiple simulations, I will need to wait a lot every single time. So like this, I need to wait like, I don't know, 3, 4, 5, 6 seconds. Yeah, now it's loaded. But with these multiple simulations, I don't waste time at all. And eventually, when I actually collected this data, I was just collecting data for 3 seconds, then click next. Collecting data for 3 seconds, click next. And it's very efficient. I managed to collect quite some episodes. The main problem for me was not the machinery, not the tools that I developed. The main problem for me was that I wasn't really good at controlling robot in simulation. So my policy became much better than me pretty fast. So I couldn't really provide a lot. I tried to collect some unusual recovery behavior, and I indeed mixed it to the training data, and I used some of it, but I'm not sure how much my policy actually learned from it. So this is actually one of the things that I would like to improve, because I think this combination of this recovery data collection and reinforcement learning is a very strong combination, because they kind of add value to each other. They have a lot of synergy. Even if your kind of recovery behavior is not perfect, reinforcement learning will make it perfect. But at the same time, reinforcement learning cannot learn this new behavior, but you can demonstrate something that works. But if you collect enough data that is good enough, then I believe it can really progress very fast. So ideally, if I had like more time, if I do it again from the beginning, I would try to combine or incorporate this data collection into the actual simulation round as well. Also, like one of the problems is probably this latency and FPS. I believe it can be improved. I didn't try. I didn't want at that point to touch the simulation logic, but I think it can be done faster. So again, I didn't try. Most probably it can be done faster, and then you can actually control robot more easily in the simulation. And again, this is something that I didn't do, but it could be the next step if I do it again. Also, it has automated simulation-based success definition. So if I actually successfully fold this garment, Yeah, you could see that I successfully folded the garment and it automatically became green and considered a success. Again, it's not a nice success. It was pretty messy, but technically it was a success. But this is one of the examples how I can define that I actually did something good. And this is it about this demonstration. So it's very, very similar to the real life DAgger data collection, with the main difference that we do it in simulation. And because we do it in simulation, we don't need to wait for the policy to make mistakes and so on. We can do it very asynchronously. And we can load only the hard states where our involvement is really required, and we can do it very fast. And it can be done pretty efficiently. And now let's go deeper into logic behind it and see how all these optimizations that I mentioned worked in the backend. You just seen how it works in practice, but I think it's very important to understand what's happening kind of behind the scene, what's happening on backend. And I made this very simple illustration. One very, very important thing, so whenever you collect data manually, you want to optimize the process as much as possible. You don't want to waste your time, because the time of manual data collection, the human time, is expensive, and you want to be very, very efficient when you're doing it. I personally solved this problem by creating multiple environments that are running simultaneously in the background and doing a lot of things like loading or saving data in parallel while I can collect data myself. So in this example, and this is usually what I use 3 workers. Each worker actually launch its own simulation engine. Each of these workers, they look at the data set, they load a new state, a new hard state that I need to correct with my human intervention. Then they're waiting until I kind of connect to them. Then I start to control the robot and collect some extra data. And then they are saving the results to the data set if these results were good and were acceptable. The most important thing that all of this is happening asynchronously in the 3 workers. So in this example, for example, my user interface is connected to worker number 1 to the simulation that is already running, that already has some garment and some hard state that I can start correcting. And I can just spend a few seconds to do it and to record whatever I want. At the same time, worker number 2 is saving my previous rollout to the disk or to the dataset, and worker number 3 may be already saved the rollout, and it's loading the next rollout to the simulation, it's loading the next rollout from the dataset. And whenever I finish with worker 1, my user interface will simply seamlessly switch to worker 3. For me, it will be just a new garment on the screen that I need to fix. But in practice, it's actually switching between different simulated environments. And actually, it's very, very nice optimization, because from the user perspective, it looks completely smooth. So you don't wait until something is saved. You don't wait until something is loaded. You simply just click the next button, and you immediately get the next garment to fold. So I really think did a good job optimizing this process. But again, as I shown you and as I said, it's pretty hard to actually control the robot in this particular scenario in simulation. And I personally control it even worse than my policy. So I didn't use it too much. But overall, again, this approach is totally applicable, and I think in many cases can be very, very useful. And yeah, so I'm a bit sad that I didn't manage to make it work, but I think I made really cool thing on the infrastructure and the overall logic side. And of course, you can check it out in my repository and try to use it yourself, or maybe adapt for your problem. Another way to look at it is this timeline. So you can see there are 3 environments, and they are always in different phases. So one environment is always connected to the operator, and this is where operator collects new recovery data. At the same time, other environments are either saving or loading data, or maybe idle when they're waiting for their turn. Another important part is to actually select the moments, the states where you want the human to intervene. So when I do it with the real robot, there is kind of no other way how to do it. I just need to stand in front of this robot in real time, watch this robot, how it completes all the tasks. And whenever it makes mistake, just click button and correct whatever it's doing. But when I deal with simulation, I don't want to do it. So I want to run many different simulations in the cloud in parallel. I don't want to look at them. I want my pipeline to be completely asynchronous, and I just wanted to select a really hard states and then give it to me for corrections. And then I don't want to wait. I don't want to watch the simulation when I'm doing it. So let's discuss how I did it. I have this rollout collection process that basically runs a lot of rollouts and save them to the training dataset. Again, I talked about it in my first videos. And I save all the rollouts, both successful and failed, because I need it for reinforcement learning. But specifically for the failed rollouts, I'm trying to detect the failure state. So I'm trying to detect the state where the actual failure happened, or maybe a little bit before, maybe a little bit after the state. And there are no super complex logic for it. I just use some heuristics. So the simplest heuristic is basically if you have some garment that is never folded properly or just has very low success probability, then just the initial state of this garment is already a hard state and you can use it. Another approach, you can look at the completion chart. And if completion going up and then suddenly goes down, or the same happens with the success probability. So success probability chart is staying high or going up and then drops more than some threshold amount, then I say that this is the failure state. So probably at this moment, my policy did something wrong. And this is exactly the state that I'm interested in, because something happened and policy now believes that the success probability is lower, or like completion percent is much lower. And if eventually this policy also failed on this particular rollout, then this state is very, very good candidate to be the this hard state that we need the recovery from. So if I cannot detect it, if, for example, I have a failure, but none of these events kind of happening, then I simply kind of forget about this failure and I don't do anything with this hard state. But if I can detect if one of these heuristics actually was triggered, then I save the exact state of the environment with all the positions of arms, all the positions of the garments. I save them into a special database with hard cases and then basically sample these cases for the manual correction. And it's happening somewhere in the cloud and simply like saved somewhere. And then whenever I want to collect data myself, I just run this DAgger data collection process on my computer, and it takes some random samples from this hard cases dataset and shows them on the screen. And then the second important thing is to understand whether my correction is actually good or not. Because as I told you, I wasn't very good at controlling this robot in simulation. So sometimes I did some corrections and they're not really good actually. So I maybe even make it worse, or maybe I didn't really fix the problem, or maybe I didn't manage to complete the task and so on. So I needed some way to say whether my correction was good or not. And there are two cases. The case number one is when I make the correction in the very end of the rollout. So for example, when I need to do the final fold, and then the environment can automatically detect the success. So if there is literally like 1 second left, like one final fold, and I do this fold and I do it correctly, then I can automatically detect success. And in this case, my rollout, whatever I did, automatically goes to the training dataset because it's completely valid success that is validated by the actual environment. But what happens if I need to make some correction in the middle of the task or in the beginning of the task? Maybe just show my policy how to fold one sleeve and that's it. In this case, I still save this rollout, but I don't directly add it to training dataset. I'm trying to feed it to the policy. So I simply start a new rollout that starts from my final state. So if I, during my data collection, folded one sleeve, then I simply start with this one sleeve folded and let policy to complete the task. If policy can complete the task, then probably I did everything fine. And my correction actually ended up in distribution for the policy, and policy managed to proceed and complete the task. If I don't know, folded this sleeve somehow not very nicely and policy actually failed in the end, then most probably I didn't do a good job. And there is no reason to have this data in the training data set, because if it's mistake, it's my mistake. It will not help reinforcement learning. But if it's not successful rollout, if it's not good, it also will not help, will not provide any recovery, any new nice behavior for the policy. So again, simply speaking, I collect partially something manually and then let policy to finish my rollout. If it managed to finish, I consider my correction good. If it doesn't manage to finish, I consider my correction bad and simply remove it. And again, as usual, everything happens asynchronously. I don't need to wait a policy to do it for me right now. I simply store them somewhere, all these not confirmed rollouts, and then run separate job to run it through the policy and to save it to the training dataset. And these are examples of the completely autonomous rollouts of my policy. This is from my home setup, and it's applied to garments that were used for training. So I collected extra data on these garments, so all of them are seen for the robot. And you may see the more or less quality of the policy. Of course, these are successful episodes. There were also failures, but I just want to show overall model capabilities when it works well. In my blog post, I share more examples of the rollouts, both successful and the ones that required some correction. But overall, this is more or less what you can achieve by training model at home using this approach that I described and using similar rig with this robot. If you're trying to reproduce it, just use these examples as a reference for the target performance. And now let's look at the official competition rollout. So this is my actual official entrance in the competition, the one that was counted towards my result. And sorry for the video quality. I was literally like running my policy with left hand and filming with right hand, and also talking to the organizers the same time and so on. So everything is very, very shaky. I didn't prepare for the nice recording when I did it, but it is what it is. I just want to quickly show you a bunch of examples so you understand how it actually worked in the real competitions during this conference. And yeah, so all these videos are 5 times sped up, so it's not the real speed. And in the beginning, you could see some successful rollouts where I get full points. And now there is a bunch of partial successes. So for example, I get probably 5 points, 5 points, and another 10 points in this case. And sometimes I get points for the sleeves, but my policy cannot finish the final fold, and again I get this partial score. And eventually I think my policy worked pretty well. It did something reasonable most of the time, but as you can see, it also made quite a lot of mistakes, and I had a lot of cases where I got some partial points only. My final score is 865 out of 1080, so I got around 80% of the maximum possible points. Let's quickly look at the final leaderboard on the official website. And as I said, I'm on the second place here. And on the first place, there is a team with a lot of people. And yeah, they're associated with different labs and companies and universities. So you can see the whole list of people from the first place here. So if you're watching this video, hi again, and congrats with your first place. And yeah, I just want to say that the first place solution actually looked pretty nice on the conference. I think the policy was even more robust, so it started to kind of correct itself a bit faster than mine, even when the small mistakes were made. So it's pretty cool, and it looked really good when we had all these rollouts. But actually, I'm not so far from them if you look at the final score. So I felt that I'm a bit farther away, but when the final score was published, I realized that actually was pretty close. So this 30 points difference, it's like the whole points for one t-shirt fully folded. So it's not so much. I think that their policy was just more accurate, and my policy made a lot of kind of intermediate mistakes, and I got a lot of partial success. But their policy just got more full success and eventually worked a bit better. I already shared my whole solution in all the details and all the possible ways. I'm not sure if the first place solution is already published and whether they will publish it, but If they will, I will add the link to the description of this video. But I know that the third place solution is actually published. It's also pretty interesting story because it was also like one-person team as me, and he couldn't actually go to the actual conference, so his friend helped him to run his final policy remotely, and eventually he managed to achieve the third place. That is very, very cool. And also his solution is pretty different. He didn't use all these things that I used, but he used some human egocentric video as an extra data for the policy. So it's interesting. I recommend you to read through it. And I will also leave the link in the description of this video. Overall, you can see that there were 8 teams in total. These are top 8 teams from the first round. And 2 of them either couldn't participate in the final round on the conference side, or there were like some technical issues with running their policies. So only 6 teams actually have some scores. And you can find the results for both rounds in this official website. We discussed everything. So I tried to explain all my main decisions in this video. Also, if you want more details, you can go and look into the code or look into my tech report. Again, everything is open sourced, and you can even try to reproduce everything I did with your robot. So as you have seen, the policy is pretty robust. So if you assemble very similar rig with the same robot somewhere at home and align the cameras and so on, then probably it will even work for you zero shot. So if you want to experiment with this, please try and let me know whether it worked or not. And let me just summarize maybe some thoughts in the end. So first of all, I believe that I used pretty nice and robust recipe, and it's kind of similar to what different companies are using right now in the industry. So I think that reinforcement learning, especially this recap and the AWR combination that I used, is very, very useful when you want to improve the results of your robot when it already can do something. So if it already knows how to fold some stuff in significant percent of cases, you can increase this percentage. And this is what I used in the simulation round a lot. And then this human-in-the-loop data correction is something that gives you a lot of exploration, that gives you some recovery behavior, because this RL that I used doesn't explore much. It cannot generate new recovery patterns, but this DAgger, the human-in-the-loop approach, can. And I think this is why this combination is really, really good. And I a little bit even disappointed that I didn't have time to combine them together. So I used a lot of reinforcement learning in the first round. I used a lot of human-in-the-loop data collection in the second. But I think if you combine them, if you make them work together, it will be even better. And it's very, very good recipe to train your robot to do some tasks. Sim and real alignment is also a very important topic. I think I covered a lot of ideas here, how you can make your simulation data more similar to the real life data. There are, of course, other ways how to do it, and there is also the whole area of real to sim that makes your simulation environment even more similar to your real one. But I didn't do these particular things in this competition, and I didn't touch it in my video. And again, none of it may be perfect, and not all my decisions were bladed, but given that I managed to achieve pretty good results in both rounds, I believe that I did a lot of really, really correct and good and important things. Maybe one thing that I would do differently is how I collected this extra data. So when I collected my recovery behavior, I actually focused on harder cases than the ones that we actually seen in the rollout, in the finals. Maybe if I spend my time just refining the simpler cases folding for my policy, for my robot, it would work better. So yeah, probably I focused a little bit on the wrong side of the spectrum of the possible cases for the data collection. And definitely, if I do it again, I would do it kind of in the more aligned way with the competition itself. But the rest is just it. So if I need to do it again, I will try to combine all the ideas from 2 rounds, try to make it one big pipeline, and just run it more and more and more, because both of these pipelines, they actually didn't saturate it. I've seen the improvements in the success rate, both in the first and second rounds when I submitted my results. So if I have more time, I can actually make it better. And again, this is maybe chance for you. So if you want to do something similar, you can start from where I ended. You can take the weights for the models that I pre-trained. You can take my code, and you can take some of my ideas. You can work on top of them. You can improve them. You can collect more data. You can iterate, and so on. So yeah, like if you want to try, just try. I kind of believe that this task is more or less solved. So if you just spend a bit more time to like refine and clean up this whole pipeline, to collect a bit more data, to train it with RL, I'm pretty sure that we can achieve much higher than 90% success rate of folding of different types of clothes using these robots. I think it's really achievable. And yeah, again, if you want to try, you can definitely do it. And that's it. It concludes my mini-series about my solution of LeHome challenge at ICRA 2026. And if you enjoyed this video and want to see more content like this, please like, subscribe, and ask any questions that you have in the comments. And see you in the next one. Bye.